But let's think about what's coming up here. We have exam 3, what, 9 days from now? Friday of next week? Then after that we have 1 class period before Thanksgiving, and then after Thanksgiving it's 6 more class periods before the final exam. I think we will, before exam 3, get through at least section 7.4, maybe some in section 7.5, which is faster than I've done in previous years. And if you look at old exam 3s in previous years, it's only through section 7.2 typically. But we will for sure get through 7.4 and maybe then a little bit in 7.5. I am purposely going a little faster, partially because I'm videotaping this year, but partially because I've always wanted to get to certain material and never had the time. Chapter 7 and 8 are pretty challenging. In some ways maybe just as challenging as chapter 5, but in other ways maybe not. It sort of depends on your personality. But I do think personally they're the most interesting chapters. And I even want to kind of transition into chapter 8, which is about something called topology, while we're doing chapter 7 some, so it's not quite as much of a shock when you get there, because it is chapter 8 is full of a lot of kind of abstract definitions and theorems. It's going to feel more like algebraic structures as far as its abstraction goes. But I think it's pretty interesting.
Yeah, I was just curious where, so since we were kind of off on the last exam, where we were ending, where do you think you'll start this exam from? 5.2 or?
Oh, from the start, okay. Yeah. For sure it'll start with 5.3, possibly some in 5.2, yeah. But again, I do think chapter 7 and 8, to me, is the most interesting stuff of the semester. And I hope, even though it's a challenge, that you'll find it interesting too. And we can start right away with these animations. I showed you one of them last time that I think are pretty interesting. I do want to do one more comparison test problem, but I think I'll save that for Friday. A little trickier comparison test problem. But I'd like to stay in chapter 7 today. I did put up Monday's Mathematica notebook on Moodle. I'll put this one up as well, although it's going to have pretty much the same kind of animations in it. Let's zoom in on the screen here. Okay, let's start big here. So we're dealing with sequences of functions instead of sequences of numbers. Okay, and so this was the first example that I showed you. The sequence of functions fn defined by the formula fn of x equals x to the n. Here we again want to make the distinction between the symbol for the function itself, the f, or in this case the fn, and its output fn of x. It's going to be important for us to really understand the distinction between those, to really make a big deal about it. We do have a sequence of functions here, not a sequence of numbers. But the functions are defined by formulas which, for given inputs x that are numbers, produce outputs that are numbers. We focus on these functions and their convergence properties over intervals. And what I have here is the interval from 0 to 1. And I've got the graph of the first function in the sequence. And there's 1 here. The first function being defined by the formula f sub 1 of x equals x to the first equals x. This is the graph of y equals x. The second function in the sequence is defined by the formula f sub 2 of x equals x squared. So if I increment n up by 1, I get the graph of x squared over the interval from 0 to 1. I left the dots from the preceding function there for a reason. Like I showed you last time, if you play this animation now to see the graph of x cubed, then x to the 4th, then x to the 5th, then x to the 6th. When you're talking pointwise convergence, conceptually speaking, you do want to focus on these vertical stacks of points. For any individual value of x, like say 0.6, f sub n of that x, f sub n of 0.6 in this case, is a sequence of outputs, y values, the second coordinates of these goldish dots. Hey, there's two slightly different gold colors. I was looking at the other one last time. Yellowish, goldish dots right here. What are their second coordinates? The first one looks to be around, well, if x, it's just 0.6, that one's going to be 0.6. That's going to be the second coordinate of that point. The second one is 0.6 squared. It's 0.36. Right there. The third one above 0.6 is going to have a second coordinate equal to 0.6 cubed. Can I do that in my head? I think I better not while we're on videotape because I'm likely to make a mistake. Somewhere around 0.2 something. 0.6 cubed. The fourth dot right there has a second coordinate equal to 0.6 to the fourth power. Somewhere around 0.15. Etc. This has got a second coordinate of 0.6 to the fifth power, 0.6 to the sixth power, etc. For that value of x, 0.6, this produces a sequence of points whose second coordinates converge to 0. But that happens for all the values of x, except x equals 1. Because 1 to the n is always 1, the second coordinate of this point stays at 1. But even though I'm not illustrating it with the animation fully, even if x are 0.99999, say, truncated, it's not repeating, it seems like it's not going to 0, but it really is. It's going to 0 so slowly. If I made some points up here that move down, they would move down very, very slowly. Slowly enough that you might think that they don't converge to 0, but they would. I just have to go out further for n to see it. I guess I could get even more extreme with n here in this animation if I went back up here and changed this from, say, a 40 to a 400. Not 409, but 400. The graph does get more and more extreme. Even when x is real close to 1, the outputs are still approaching 0. It still passes the vertical line test. No vertical lines going to go through it more than once. But when x does equal 1, or 0.9 repeating, right, because 0.9 repeating equals 1, the output is always 1. So this sequence converges pointwise to a discontinuous function. The function that is 0 between 0, including 0, but not including 1. From 0 to 1, including 0, but not including 1. And at 1, the function value of the function it converges to is 1. But we can also consider the same function over different intervals. Here I'm considering the same function over the interval from 0 to 2. So let me go back and make this up. Over the interval from 0 to 2, what happens? When x is bigger than 1, the second coordinates of the points go up. Forever and ever, they diverge to infinity. So over the interval from 0 to 2, this function, this sequence of functions, does not converge pointwise to some function over that entire interval. Unless you decided to allow infinity to be considered as a possible function output, but we are not. It does have kind of a nice spiraling effect there, visual spiraling effect, but you do want to focus on the vertical stacks. What are happening to the second coordinates of the points, the outputs, for given values of x along these vertical stacks. When x is bigger than 1, they're going up forever and ever. Fn of x is diverging to infinity when x is bigger than 1. So you would say this sequence of functions over, the same sequence of functions over this bigger interval does not converge pointwise to any function over that interval. Once again, same sequence of functions. This time now the intervals from -1 to 1. Keep raising negative numbers higher and higher powers. Sometimes the output's positive, sometimes the output's negative. We're going to get a tail wagging effect on the left. So in this case now, when x is negative, say not equal to -1, focus in here, say maybe right there. Maybe I should slow this down, I think. Okay, I'll wait till it comes to the end here. Now, here we go. Focus right here, say, at x equals 0.5. I didn't go fast enough. The outputs are jumping up and down, oscillating, but they are still going towards 0. We'll wait for it again here. When x is 0.5, we have 0.5 to the first power first. When n is 1, that's, excuse me, negative 0.5 to the first power. That's the second coordinate of that point. Then negative 0.5 to the second power is 0.25. It bounces back and forth. It's oscillating, but it is still converging to 0. At -1, however, we get the sequence -1 to the n. Bounces back and forth between -1 and 1. It doesn't converge at -1. So the biggest interval on which you could say this sequence of functions converges would be the interval from -1 to 1, not including -1, but including 1. For this particular example, you could say this sequence of functions, fn, converges pointwise to f on the interval from -1 to 1, not including -1, but including 1, to the function f defined by piecewise formula f of x equals 0 if x is strictly between -1 and 1, and 1 if x equals 1. That is the pointwise limit of this example's sequence of functions. I'm talking about this example here, defined by that formula. That's the biggest interval on which it converges pointwise to some function. Do put the word pointwise in there, because we're going to distinguish pointwise convergence of a sequence of functions with something called uniform convergence of a sequence of functions, which is analogous in some ways to uniform continuity. Not the exact same concept for sure, but somewhat analogous. Here's another example. Actually, these examples are taken straight from the book. We're looking at that list of 7 examples that the author mentions. The sequence of functions fn defined by fn of x equals x over n. Do write all these things out in the way that we're writing. Okay? You got to make the conceptual distinction. We are focused on the sequence of functions itself and its convergence properties. Functions are often defined by formulas. This is not the function here. This is the formula that defines the function. It's a subtle difference that we usually don't make too big a deal of, but it does make a big deal here if you're going to really understand how to say things. The interval I picked was -10 to 10. There we go. Looks like that sequence is converging to the 0 function over the interval from -10 to 10. And it would converge to the 0 function defined over the entire real number line to converge pointwise. I picked -10 to 10. I could have picked a bigger interval. It would still converge to the 0 function. When x is further away from 0, the convergence is more slow. But for any x, for any fixed x, this expression, x over n, as a sequence of numbers for any fixed x, does converge to 0. Right? For any fixed x, x is 10, x is a million, whatever, that sequence of numbers, if we considered it to be defining a sequence of numbers, would converge to 0. And that does mean this sequence of functions converges pointwise to the 0 function, the functions whose outputs are always 0. Its graph is the x-axis. Next example. Let's try to predict what's going to happen. You can see this looks more complicated. Let's try to predict what's going to happen. The sequence of functions fn defined by this formula. Are we zoomed in enough to see that okay? Good? Okay. Certainly, let's consider simple cases. When x is 0, that expression always equals 0. So if this sequence is going to converge pointwise to some function, when x is 0, that function must have an output of 0. Catch what I said there? If this sequence is going to converge pointwise to some function, because this expression is always 0 when x is 0, that function it converges pointwise to must have a value of 0 when x is 0. What about when x is 1, another simple case? 1 to any power is 1. So n is irrelevant in that case. When x is 1, this is going to give you 1 divided by 1 plus 1, 1/2. It always equals 1/2, no matter what n is. So once again, if the sequence of functions does converge pointwise over some interval, the value of the limit function at 1 will have to be 1/2. Those are the two simplest cases. I suppose we could consider -1 as another case here. -1 to powers here are either going to be, those are integer powers, are going to be plus or minus 1. And actually those powers, because it's 2n plus 1, are always odd powers. Which means -1 to that power will be -1. Which means it's not going to be part of the domain of this function to begin with for any n. Looks like -1 is out as a possible place where the sequence of functions could converge. Functions in the sequence themselves are not even defined at -1. How about if x is between -1 and +1 strictly? Like 0.5, -0.7. I'm raising those kinds of numbers to higher and higher powers. You should know, we know, but that goes to 0. As n goes to infinity, when you raise a number like 0.5 to higher and higher powers. So even though this function for any fixed n does not equal 0 when x is 0.5 or -0.7 or whatever, as long as x is not 0, this expression does go to 0 as n goes to infinity. So it seems to me we're starting to get a picture of this sequence converging to a function whose graph is 0 when x is strictly between -1 and 1. It's not defined at -1, but at x equals 1, the output is 1/2. Yeah, over the interval from -1 to 1, not including 1, but including +1, not including -1, but including +1, this will be the limit function, the pointwise limit function. Could it possibly converge when x is bigger than 1? Like 2 or 3? It does actually in this case. Say for x equal to 2. 2 to the 2 to the n plus 1, 2 to the 2n plus 1 gets bigger and bigger and bigger as n goes to infinity, but it's in both the numerator and denominator. And the plus 1 is kind of irrelevant almost to the limiting value of the function in that case. Essentially, you get something close to 1 when n is large, even if x is bigger than 1. And that would work for any x bigger than 1. Seems to me the limit function is this function, at least when x is bigger than -1. How about when x is like -2? We are racing to odd powers here, so you get negative numbers. It seems like maybe that it should converge when x is less than -1 as well to 1. The book doesn't mention that. And I'm only plotting this over the interval from -1 to 2, but maybe I should make a bigger interval here. I only made my dots there, but I guess I could fix that probably. Let's see. Well, I would want to avoid -1. Let's not worry about the dots when x is less than -1. There's what the graph looks like when n is 1. When x is to the right of -1, and evidently there's a vertical asymptote of -1. We've got the graph over here as well. What happens is you let n get bigger. Yeah, it does look like the graph is converging to -1 over here as well. Again, make sure you think about this in the right way. For any fixed value of x, you focus on the second coordinates of the points. What's happening to these vertical stacks. When x is in here, the outputs are approaching 0. When x is over here, the outputs are approaching 1. When x is 1, the output stays at half all the time. At x equals -1, none of these functions are defined, so it can't converge to anything if it's not defined. It does look like when x is less than -1, we get convergence to 1 as well. Even though the book didn't mention that, that's why I wasn't thinking about that at first. But that does look to be the case. This one's a little different. The formula for Fn, the ultimate formula you might say, doesn't actually have an n in it. But the domain, and therefore also the overall formula, is dependent on n. So the domain on which this formula is valid depends on n. So the convergence is a little different in this case. When n is 1, looks like we have the 0 function. Does that make sense? When n is 1, 1 over n is also 1. The output would equal sine of pi when x is 1, which is 0, and otherwise also equals 0, so this should not be a surprise. When n is 2, this becomes 1/2. The function is going to be 0 between 0 and 1/2, and equal to sine of pi over x between 1/2 and 1. Increment n up by 1, we get this. A sine of pi over x. X goes between 1/2 and 1. When n is 3, we get 0 when x is between 0 and 1/3. And sine of pi over x when x is between 1/3 and 1. Yeah. And then the sine of pi over x, essentially this graph keeps moving to the left because we keep defining it over bigger and bigger intervals. When n is 4, it goes from 1/4 to 1. It's the graph of sine of pi over x. When n is 5, it's 1/5 to 1. The domain of the sine of pi over x part of the formula. When n is 6, it's 1/6 to 1, then 1/7 to 1, and then 1/8, then 1/9. It's not graphing it very well here. If you pause it at any point, then it takes a few seconds and graphs it better. This is one of those infinitely oscillating functions if you define it over the entire interval from 0 to 1, by the way. We've done the sine of 1 over x before. Sine of pi over x is not that much different. The convergence here is a different kind of thing. For any fixed x, typically there's only 2 outputs. 0 and whatever else it is when n is sufficiently large. X equals 0.6, for example, the second coordinate starts out at 0 when n is 1, then becomes around -0.85 when n is 2, n3, n4, n5, n6. So the graph is changing more in its domain than sort of up and down as n increases. domain where the formula sine of pi over x is valid. So this is not converging to the 0 function. It's converging to sine of pi over x when x is between 0 and 1, not including 0. What about when x does equal 0? Looks like it's staying at 0. If you look at the formula here, yeah. The output of fn at 0 is always 0, no matter what n is. So it's converging to the function that equals sine of pi over x when x is bigger than 0 but less than or equal to 1, and the function equals 0 when x does equal 0, the limit function. Another piecewise example here. Let's not bother thinking about this one, though you could. Let's just see what happens. Each fn of x has a graph that is a isosceles triangle from 0 to some number and then 0 afterwards. So the visual effect with the graph is that it sort of moves to the left. But again, as far as pointwise convergence goes, you want to focus on each individual x. Like 0.6. When n is 1, the output is 0, but then it jumps up to around 0.2. Then it jumps up to here next, I believe, to around 0.8. Then back down to there. No, excuse me, sorry. I guess it's 0.6. Then it jumps up to that, because the second function is straight like that. Then it jumps up here, because the third function is this isosceles triangle. Then it jumps back down here. The fourth function is a graph. This isosceles triangle, something about like that. Then it jumps back down to 0. When x is 0.6, the outputs go here, 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 and then back down to 0 thereafter. When the output, when x is 0.4, when n is 1, the output is 0, then it jumps up to there, then there. It stays there, it looks like, when n is 3 and when n is 4, because it looks like that point right there is both a part of this graph and a part of this graph. Before it comes back down to there, and then back down to 0, and stays at 0 thereafter.
Why did it start at 0?
When n is 1, it's the 0 function. Oops, I guess I was wrong. Thanks for pointing that out. I was thinking it was the 0 function to begin with. I was wrong. Thanks for pointing that out. It doesn't start at 0.
What function is it?
We see that function.
Looks like it's the function y equals x, perhaps. When n is 1, this is a 1, and the formula is x there. I guess it would be defined in a bigger interval, like from 0 to 2. When n is 1, you use this formula between 1 and 2. I only graphed it between 0 and 1. Although I guess, when n is 1, this formula is not fully valid, it looks like. Because when n is 1, this doesn't make any sense. This formula is not really fully valid as stated. When n is 1, for sure. Here's the last example. This one's a piecewise one too. Again, let's not worry about the details of the formula. Let's just look at the graph. There's the graph when n is 1. As n goes to infinity, it approaches the absolute value function. That's what's happening here. When x is less than -1 or bigger than 1, it looks like the function always equals the absolute value function. I guess that's not surprising when you look at the formula. The only interesting stuff is when n is between -1 and 1. then the outputs are increasing to the absolute value function. Interesting here, you got a sequence of differentiable functions converging to a function that's not differentiable over the entire interval. Back way up here, say our first example. You got a function, a sequence of functions, all of which are continuous, converging to a discontinuous function. It's even more extreme, perhaps, with that other example that where it, let's see, does this one. Focus when x is bigger than -1. It's a sequence of continuous functions converging to a discontinuous function. That doesn't seem good. That properties like continuity and differentiability are not being preserved for the limit function. We would like them to be preserved, wouldn't we? And the moral of the story there is pointwise convergence of a sequence of functions is not enough in general to preserve nice properties. We need some sort of stronger convergence, and that's called uniform convergence. All right, let's actually write some stuff on the board now. Some definitions. First of all, what is a sequence of functions really? I'm not going to state it as a typical kind of definition. Let me write a question. What is a sequence of functions? Should I add the word really? Yeah, for emphasis. Really. Well, before we try to answer that question, we should probably try to answer the question, what is a sequence of numbers, really? The simplest way to imagine a sequence of numbers is just a list of numbers that goes on forever. But that's not what it really is. When I say the word really with extra emphasis, I mean technically, mathematically, rigorously. I did mention this back in chapter 2. A sequence of numbers is really a function. A function whose domain is the natural numbers and whose codomain is this entire set of real numbers. We write it like that. It's just a symbolic representation of a function. For any positive integer n, any natural number n, you get a number s sub n. So it's really a function. A sequence of numbers is really a function whose domain is the natural numbers, which is the same as the positive integers, and whose codomain is the entire real number line. I should say the entire set of real numbers. So what is a sequence of functions? Well, you could intuitively think of it as an infinite list, f1, f2, f3, f4, etc. But what is it really? Technically, mathematically speaking, rigorously, it's really a function. Not a function like one of these, though. It's a function of the form of something that maps the natural numbers, also that's the positive integers, into what? Into some function space. What? Function space? What is a function space? Okay, it's just a fancy name for a collection, a set of functions. Though it often has nice properties. It's a certain special class space of functions. For example, maybe the set of all continuous functions on some closed interval. Or maybe all the set of differentiable functions on some closed interval. Or, thinking even more broadly, maybe just all the set of all possible functions on some closed interval, which would include plenty of discontinuous and non-differentiable functions in it. That's what it really is. A domain natural numbers, codomain, some function space. I do want to use this terminology, not just today, but here in the future. So this is part of leading us into chapter 8 about topology. All right, but we often aren't thinking so fancy. We're often just thinking of it as a list, an infinite list, and we use this notation analogous to this notation. But these are, the outputs of this sequence are numbers, the output of this sequence, the outputs of this sequence are functions, ordinary functions, f sub n, defined at some interval. Real valued functions defined at some interval. Here's a definition. We say a sequence of functions fn defined on some interval I converges pointwise to a function f defined on I if for each x in I the sequence of numbers fn of x converges to f of x. Converges as in chapter 2. This is a sequence of numbers. And that's a number for any fixed x. i.e., for any fixed x in I, you could say that the limit as n goes to infinity of the function outputs fn of x equals f of x. That's what we're thinking about with those vertical stacks. Different fixed values of x. What's happening to the outputs of these functions? Are they converging to something? Call that something f of x. If they converge to something for each x in some interval, then you say that the sequence of functions converges pointwise on that interval to the function whose outputs are those values of f of x. Pointwise convergence is not good enough to preserve nice properties. In general, it may for particular examples. Something called uniform convergence is good enough. Another definition. A sequence of functions, I'm going to do more abbreviations here. Fn defined on some interval I. I is assumed to be some interval. It could be an open interval, it could be a closed interval, it could be half open, half closed. It could be the entire real number line. Converges uniformly, not pointwise, but uniformly, to f defined on I, if what? Well, back here in the definition of pointwise convergence, for each x, this sequence of numbers converges to that number. But the rate of convergence could be a lot different for different x's. We saw that with those examples. The very first example, when x is between 0 and 1, including 0 but not including 1, the convergence of the points down towards 0 was much slower the closer x was to 1. intuitively, that's not uniform convergence. You want the rate of convergence to be roughly, you might say, the same for all x to get uniform convergence over the entire interval. Similar to the idea of uniform continuity, analogous, not exactly the same concept. With uniform continuity, you want the delta that you picked to be independent of x, to work over the entire interval. Remember uniform continuity? There's an epsilon and delta in the definition. You want to make the function outputs within epsilon of each other as long as the inputs are sufficiently close within delta of each other over the entire interval. It's an analogous idea here. If for all epsilon greater than 0, we are dealing with a sequence here. There's going to exist a capital N, not a delta. There exists a capital N such that the distance between Fn of x and f of x is less than epsilon, not only for all little n greater than or equal to capital N, but also for all x in the interval. And it's that for all x in the interval that's the key. So the capital N that you pick depends only on the epsilon, not on x. That's uniform convergence. If a sequence of functions converges uniformly to some function on some interval, it also does converge pointwise. Okay, this is still going to be made small if little n is large enough. That's good enough to prove pointwise convergence. But pointwise convergence does not imply uniform convergence. Question?
Yeah. What would f of x be in this case? Is it the function that it is converging to, or is it like f0?
It's the function that the sequence of functions is converging to, yes. But it's converging to it in a stronger way.
Okay.
Do you have a visual representation
Uniform
of that?
convergence. What?
Do you have a visual representation of that?
Yeah, okay, let's come back to our examples. This example is not uniform convergence. Intuitively, for a given epsilon, like epsilon is 0.1 for example, you're not going to be able to make all the output values of fn of x within epsilon of the limit function if n is sufficiently large for the entire interval. If n is sufficiently large, you may be able to make, say n is the biggest value here, 40, and epsilon is 0.1. You're going to be within 0.1 of the limit function when x is between 0 and, well, 0.9 for sure, but it looks like 0.95 is not quite within 0.1 of the limit function. The output f40 of x is not quite, or maybe just barely, within 0.1 of 0 when x is 0.95 here. I'm sure when x is bigger than 0.95 but not equal to 1, the outputs are definitely further away from 0 than 0.1. At 1 it always is 1, so there's no problem there. But it looks like for x between about 0.95 and 1, when epsilon is 0.1, 40 is not good enough. Then you'd say, well, what about a bigger n? Well, yeah, you'd be able to get, say, this one within 0.1 of 1, but then there'd be points over here that are still not within 0.1 of 1. 0.1 of 0, I mean. Talking of vertical distance there. So that's not uniform convergence. Are any of these examples uniform convergence? This one is as long as you have a finite interval. I said that we got pointwise convergence in this example to the 0 function over the entire real number line, but it's not uniform convergence over the entire real number line. But if you restrict yourself to some closed and bounded interval, like from -10 to 10, you can say it's uniform convergence over that interval, even though the outputs at 10 are converging more slowly at 10 and -10 than they are when x is close to 0. You still, for a given epsilon, say epsilon is 0.1, over this interval can choose n sufficiently large to make the outputs all within 0.1 of 0 over this entire interval from -10 to 10. So even though they go more slowly at the endpoints, it is still uniform convergence over this interval, but not over the entire real number line. The domain is important. Just like always in real analysis, it's not just the formula, it's the domain. You got to always refer to the domain that you're talking about. This one's not uniform convergence. When x is close to 1, it takes longer for your outputs to get closer either to 0 or 1, depending on which side x is of 1, to the left of 1 or to the right of 1. And yeah, you can't choose a capital N that works for all x. This one does not converge uniformly, I believe, but it's harder maybe to explain. Maybe I'm wrong. Could it possibly converge uniformly on this entire interval? Well, no, it doesn't. For a given epsilon, if you choose capital N pretty large, you're still going to have points close to 0 that are not close to their, not within, for example, 0.1 of their ultimate outputs along the graph of sine of pi over x. Even for arbitrarily large n, you're going to still have points close to 0 that are not close to their ultimate outputs, their outputs for the limit function. So this is not uniform convergence. This one is not either, because no matter how large n is, you've still got outputs close to 1 and even equal to 1 for some x's. So that's not uniform convergence. This one does appear to be uniform convergence. We're still losing the differentiability of the limit function at x equals 0. I think what is not quite good enough to make that happen is maybe also the derivatives of these fn's are not converging uniformly. The fn's themselves, I think, are converging uniformly, but perhaps their derivatives are not. I'm not quite sure. And that might be why we're losing the differentiability at 0 in the limit function. If we can do sequences of functions, we can also do series of functions. Because after all, series are related to sequences, right? A series of functions is an expression of the form summation k goes from, well, either 0 to infinity or 1 to infinity. I'll write 1. As this stands, it's just a symbol. It doesn't necessarily mean anything. Might not converge. We say the series, don't write curly braces like I almost did there. converges pointwise to some function. Should I call it f still here? Maybe I'll call it g. On some interval I, if the sequence of functions that are the partial sums of this series, and here you do need the curly braces. By the way, this, in case it wasn't clear, this is an abbreviation for functions. Sequence of functions converges pointwise to g on I. Sequence of functions where each function is a partial sum of the series. Just like with series of numbers. And it's going to converge uniformly. I won't bother writing this down. This series is going to converge uniformly to g on I if the sequence of functions that are partial sums converges uniformly to g on I. Maybe I should put slash uniformly. It's two distinct definitions. Just change two words from pointwise to uniform. Let's finish today with an example. Quick example.
So it says in the book that it converges, or the corresponding sequence of partial sums converges.
Yeah, that's the sequence of partial sums. Yeah, just put the notation in there. They just describe it in words, is that what you're saying?
Or they did both, yeah.
Let Fn for each positive integer n be defined by Fn of x equals, let's say, x over 8 to the n. On the interval I equals, let's say, it's the open interval from -8 to 8. Consider the series, maybe I should use the k, oh well. The sum of these things. The partial sums, okay, let's not even bother with the partial sums. No, we better focus on the partial sums. The partial sums, should I use k or n? Okay, let's change these to k's. Sorry. K goes from 1 to n of fk is a function whose value at any value of x is what? This is a function whose value at any x is what? Use the formula now. It's this sum. And that sum is a finite geometric sum with first term x over 8 and common ratio x over 8. And we know that that equals, as long as x is not 8, x over 8 times 1 minus x over 8 to the power that is the number of terms there, that is n, divided by 1 minus x over 8. If x is not equal to 8. And if x is strictly between negative 8 and 8, as n goes to infinity, let n go to infinity. This is going to go to 0. This is going to converge to 1 minus 0 up top there. You're going to get x over 8 over 1 minus x over 8 when the absolute value of x is strictly less than 8. We're in I. And this simplifies to x over 8 minus x. Which for a fixed x is just a number, but hey, I could let x be anything between negative 8 and 8. And therefore, I could think of that expression as defining a function, f of x, or g of x, if I'm going to be consistent with this notation, g of x equals x over x minus 8 minus x. That's a function. That's the formula for a function is what I should say. It converges pointwise. Does it converge uniformly? It turns out no, it doesn't converge uniformly. And intuitively, the problem is near 8 because you got a vertical asymptote for the limit function. However, if you consider some subinterval of this that is a strict subinterval, not equal to the entire interval, it would converge uniformly over that subinterval. But you're not worried then about the vertical asymptote question.
I noticed that you use the absolute value of x, so I was curious about negative 8, but then,
Yeah, the absolute value of x being less than 8,
yeah.
it means x is between negative 8 and 8. So I think the trickiest thing here is the language. Getting this language right, distinguishing between functions and their outputs. That's perhaps the trickiest part. So really read your reading carefully as you start to work on chapter 7. I mean, you've worked on it some already. Continue to do your reading carefully. See you on Friday.